So here we're going to be solving both problems 23.43 and 23.44 of this problem. So here we have a sphere of radius r that surrounds a particle of charge q located at its center. And we want to figure out the electric flux through a circular cap of half angle theta. So essentially we have this hole inside of our sphere, and we want to figure out how many of the electric field lines are exiting through this sphere. Essentially, all we need to figure out is what is the surface area of this hole in the top. So to do so, I've drawn it out like this, where I'm going to divide up this hole, or this cap, right, into little circles that are spaced by distance ds. Now, if we remember, ds is going to be a little step along the arc length. It's a little segment of the arc length, where r theta is a component of the circumference, that here we have the radius we have in making an angle theta, and this part of the circumference is just going to be equal to r times theta. Then ds, which is a step along the circumference, is going to be equal to radius times d theta. So that's what ds is. Now remember that theta is in radians, and ds is our little arc length step. Now, the area of each one of these strips here is going to be equal to the circumference it makes times ds, its thickness. Now, their circumference is equal to 2 pi r, where we define here r to be the radius of one of these circles. Now, remember that each one of these circles has a different radius, so little r is going to change, right? Well, how is it going to change? It's going to change with theta. So here we have little r is equal to r sine theta. If we define big R to be going from the center of our sphere all the way out to the little strip that we're talking about, so that's big R. Theta is going to be the angle between the center y-axis and the edge of our strip, and then little r is its radius. So then we know that, okay, little r is equal to r times sine of theta. That means C, our circumference, is equal to 2 pi capital R sine theta. We multiply that by ds, which we know is capital R d theta, and we get this, 2 pi capital R sine theta r d theta. Now the idea here is that the surface area is going to be adding up all of these strips, right? So essentially what we're going to be doing is starting out at theta is equal to 0 and going all the way to theta is equal to, or angle is equal to theta. By that, I mean here, we're going to start off by, I'll draw that out here. We're going to start off by considering the first tiny little circle here, and then we're going to take a step out to the side, and we're going to draw another circle here, figure out its area, draw another circle here, get its area, draw another circle, its area, and we're going to go from theta is equal to 0 to, well, theta is equal to theta. By that, I mean we're told what it is in this problem, which is 45 degrees. All right, so we're adding up all of these little circles like this. So then our integral goes from theta is equal to 0 to theta is equal to theta. We take out all of the constants, so we have 2 pi r, those are all constants, and then we have 2 pi r squared here, integral of sine of theta d theta from 0 to theta. All we do here is take the integral of sine of theta, which is negative cosine of theta. We evaluate it from, theta goes from 0 to theta, and we get 2 pi r squared negative cos theta plus 1. So then A is equal to this here. Now that was just figuring out what the surface area is. We want to figure out what the flux is. So if you remember, flux is equal to E, because here, if we remember when we're dealing with spheres, we have this E dot dA, but we know that the electric field and the dA components are going to be in the same direction. So that gives us this. And we also know that the electric field is going to be the same at every single point, because here, remember, we're dealing with positive charge and we're dealing with a circle. So it's all pointing radially outwards in the same, like this electric field component's the same as this electric field component, and so on and so forth. It's pointing out radially with the same magnitude everywhere. So that is what lets us go from this to E, dA. And this here, this is just our surface area, which we've already calculated. So then our flux is going to be our electric field times our surface area here.